So lever systems, where we're starting to deal with, how the skeletal and muscular system work together in different ways to produce different types of movement. So we'll go through from this. So hopefully by the end of this, move that there, we should know the 3 different classes, 1, 2, and 3. We should be able to draw these and label them appropriately, and then hopefully some people might even be able to sort of apply lever systems to the body itself in a sporting situation and be able to talk about mechanical advantage, what it is, how we can achieve it, and what impact might it have on sport. There we go. So that's quite a nice quote that I like to start levers with. Archimedes being sort of an old school scientist, mathematician, give me a lever long enough and a fulcrum on which to place it, and I shall move the world. Postulating that anything is movable, any amount of force can be generated with the correct lever system. Okay, and you've got 3 components here. Just a bit of a heads up. We've got the Earth, we've got this pole, and we've got the thing on which the pole is rotating on. So we've got the Earth, the pole, this thing where rotation is going to be happening, and we've obviously got the people as well. So hopefully by the end of this, you'll be able to actually label this diagram, not just see it as a bit of an introductory quote. So lever system, what is it? Well, it's a rigid but movable structure. Okay, rigid but movable. So the components of a lever typically are solid. Okay, they're typically hard, tough, but together they can articulate around each other to create a movement. So within sport or within anatomy, we've got bones, solid. We've got muscles, which can produce force, but where they attach to the bone, the tendon, that's fairly tough and fibrous as well. And then we've got the meeting point of bone on bone. Again, a very solid structure. So whenever we move, be it exercise, be it sport, be it walking, be it standing, doesn't really matter, be it move my arms, there's levers at play. We've just come from the skeletal lesson there, where we're talking about attachment and movement and how we can produce different actions using our skeleton in conjunction with our muscular system. Well, how do we actually, what's the secret sauce between how they actually interact? Well, it's levers. Different bones and different muscles are capable of different speeds and magnitudes of movement based on the lever system that they're in. So we're going to look at different types of levers, because they're not all created equal. None of them are good or bad, but they have good situations and bad situations where you might choose to use them in real life. Obviously, with our skeleton, it's built the way that it's built, so we can't change the class of lever, but it's good to understand how they're working, how they're at work, so we can apply that to our training. So we've got scissors here, for example. Obviously, we've got that point in the middle, which isn't moving. We've got the 2 rigid parts or 2 rigid halves of the scissors which do move, and we apply force through them. We can lever 2 pieces of metal together so that we can cut through paper. A wheelbarrow. We've got a wheel that stays on the floor. We've got the barrow part, we've got the bucket part, which we can load up. And then we've got the handles that we can lift in order to move stuff or to tip stuff. And we've also got a bit of a science experiment here. If you've ever got a spare 5 minutes, this is quite interesting. But it's a marshmallow catapult. So with a couple of sort of skewers, you can create this tripod, and you can generate force with. If you can see that, there's a rubber band attached to one of the that moving catapult arm. Marshmallow on the top, we pull it down, we let it go, and we can generate movement. By attaching things together, by moving them in a certain way, we can generate force to move something else. It's all about this transfer of effort in one area of the lever to create an output of effort to overcome something in another part of the lever. So for the wheelbarrow, if we apply effort to lift the handles, we can overcome the resistance that's in the barrow, in the bucket. Scissors, we apply force through the handles so that we can pinch with metal on paper to cut. We've transferred energy from fingers into the cut. So it's this transfer of force application. And if we were to simplify these onto a drawing, now I know if you haven't seen these already, they can look a bit much straight away. But this is them in picture form, in diagram form. So if we take the orange one there, the scissors, and that triangle, if you were to imagine that in the middle of a seesaw, or that center point on the seesaw isn't actually moving. It's the pivot. It's where the rotation is actually happening. And if we think about the scissors, at that central point, there isn't movement happening. It's the rotation point. On the second one across, if we take that triangle again, okay, that pivot point, or if that's the point that wasn't moving or isn't moving, if we have a look at the wheelbarrow, it's not the wheel on the wheelbarrow isn't moving either. So in our levers, we've got an axis, a point of rotation, a pivot point. Axis, pivot, rotation. And then in that blue example, where we've got that square at one end, we've got the point of rotation at the other, and we've got this catapult action. 3 different types of lever, 3 different ways that structures can move around each other. We can apply a force to a structure to generate an outcome. So the first thing that we have is a lever. Okay, the lever. This is this rigid bar or structure or an arm. It's rigid and it's fixed to, now that word there, fulcrum, we'll cover it in a second, but that's our pivot point. So the triangle in this diagram, that's the pivot. That's where rotation is occurring. The lever is that darker orange bar. So the lever sits on top of something which it can pivot around. Now it might sit on top at one of the ends and it rotates around it like that. That's what makes different levers different. So we have a lever, we have a fulcrum, which is that pivot point. We have effort, which is production of energy or the release of energy into the structure or the lever system itself. And then we have the load or the resistance that we're working against. So if we take this example here, the one just above the green box, we've got that pivot point with the lever sitting on top, so this seesaw action. But if we were to apply effort and pull one end down, it's going to rotate around the pivot and it's going to cause this up force or this uplift on the box which is on the left-hand side, which is currently weighing down because of gravity, hence the downward arrow. We've got a load or a box or a piece of resistance with gravity's pulling it down. We've got the arm or the lever that it's sitting on top of. We've got the effort that we pull down on, and with that fulcrum in the middle, we generate that seesaw catapult action. So a downward force one end can transfer into an upward force at the other. So we've got the lever, the fulcrum, effort, and then the load or resistance. Now I'm going to be keeping those, what's the phrase? Those diagrams, those shapes, let's say, they're going to stay consistent. Okay, so just have a little look now and remember those. Lever, fulcrum is the triangle, effort is that downward arrow or upward arrow. Okay, effort could be down or up. It just depends on how you draw and how the lever is set up. But effort is a standalone arrow, and then the load or resistance is typically drawn as a box with a downward arrow. So here's one in diagram action. Everything that we've just spoken about. So the person on the right hand side, they are applying downwards effort, hence the arrow is going down. We've got the pivot or the fulcrum underneath this plank, underneath this lever. And by pushing down at one end, The pivot is going to sit in the middle, and that's going to allow us this downward action at one end from the person. We push it down, and it's going to lift the other end of the plank up and overcome the load which is sitting on the other end of the plank. Okay, this is how you'll need to draw, or not this exactly, more like the orange one at the top there, but this is how you'll need to draw your lever diagrams in your exam. Line, triangle, effort arrow, load box, and the load arrow. And you need to make sure that the arrows, and you need to make sure it makes sense, basically. Is your effort arrow pointing in the way that's going to move the lever to actually overcome the box? So it wouldn't make sense here for this person to lift up. Because if that person lifts up, well, that's going to lift it's going to rotate the lever the other way, and it's not going to work. So we need to make sure that we draw it in the right places. But this person could choose to move this plank, to move the pivot, to move the box, to move themselves, and create a new lever system. So they're not all the same. So let's have a look at how this person could have changed it up. Well, that middle option there, if they wanted to lift this box, then they could have set the pivot up, or this lever up, by having the fulcrum at the other end and the box in the middle, and then he's lifting from the other end. He could have stood in the middle with the pivot behind him. He could pull on that plank of wood and try and lift the box, which is at the other end. So all three of these could have happened, but they've decided to go for the one at the top. Now try and put yourself in this situation. I'm wondering now, if you imagine yourself doing this, which one do you think would be the easiest? If you need to lift, what's that, times 250. Let's say this was 200 kilograms. That's about just under 3 of me. That's a lot. That's quite a lot of weight. So do you think you could lift 3 people using option 2 or option 3? You might be thinking yes or no. Hopefully you're thinking it's going to be harder with option 2 and option 3, but you might not understand why. That's what we're going to be covering today. So a lever system is this transfer of force and effort in one direction to generate the output of force at another part of the lever system to overcome a resistance, to overcome an effort, to overcome a load, I should say. So the person pushes down in that first option to be able to lift the box up. 1, 2, 3, option 1, 2, and 3. Like we just said, some of them are going to be easier, some of them are going to be harder. None of them are necessarily good or bad, but they might suit different situations because they have different characteristics. So, labeling a linear version of a lever system. Well, we have, I've already said, 3 systems. We have a first-class system, we have a second-class lever system, and a third-class lever system. Easiest way to remember which one is which, either when you're looking at it, or you have to draw it, or whatever it is, FLE 1, 2, 3. I'm even going to put that behind me just so it's always there. FLE 1, 2, 3. Now you might have noticed FLE refers to our definitions: fulcrum, lever or load, effort. So fulcrum, load, and effort. Fulcrum, load, and effort. Whichever component is in the middle of the lever system, that corresponds to the letter. So FLE, 1, 2, 3. When the fulcrum is in the middle, it's a first-class lever. When the load is in the middle, it's a second-class lever. When the effort is in the middle, it's a third-class lever. So straight off the bat, let's look here. On that option 1, the pivot or the fulcrum. The fulcrum's in the middle. FLE, 1, 2, 3. F1, that will be a first-class lever system. Then we changed it around, option 2, where the load was in the middle, FLE, 1, 2, 3. If the load's in the middle, it's number 2, it's a second class lever system. Different to the first one, different benefits, different drawbacks. And then the third one, FLE, 1, 2, 3, effort is now in the middle. The person pulling on the plank is now applying the effort in the middle of this whole structure. So definitely the best way to remember. FLE 1, 2, 3. And there we have them in diagram format. So first class, where we have that fulcrum in the middle, if we pull down, that allows us to catapult upwards and overcome the resistance at the end. Second class, FLE 1, 2, 3. So the load is in the middle, it's sitting on this plank, and it's weighing it down. Fulcrum and effort can be either way round. Doesn't matter, because we're pulling on one end and we're gradually lifting up, almost like hinging it up. And then third class, FLE 1, 2, 3, the effort is now in the middle. So that's our lever. The effort is pulling from the middle upwards. Let's say the elbow is the fulcrum at one end. We pull and we lift up. We lift up, and the resistance or load is going to be in my hand. Now, how are they different? I know that if we move things around, and I said there's benefits and drawbacks. Well, the key thing that you'll need to know for your exam is all to do with this mechanical advantage. What is it? How do we calculate it? Why does it matter? Well, it's down to these two things, the effort arm and the resistance arm. Now, the effort arm is the distance from wherever the effort is applied on the lever. It's the distance from that point to the fulcrum, to the pivot. And the resistance arm is from wherever the load starts, the center of mass of the load of the resistance, the distance from that to the fulcrum or the pivot point. So what you can see here is in this lever system, FLE 1, 2, 3, F, fulcrum is in the middle, therefore this is a first class lever system. We've got a large effort arm and a short resistance arm. Okay, they're unequal. They're unequal. Now this is good for us. This is good. I'll tell you why. Oh, where do we go now? Well, I'll tell you why it's good in a moment. But just so you can see sort of how this mechanical advantage can differ between classes, we'll look at this slide here. So if I quickly jump out, the slide, where do we get to? There we go. Right. So as the fulcrum moves, so fulcrum here is in the middle, first class lever. Well, if we were to move the fulcrum sideways, to a different point on the lever, suddenly the effort arm is shorter and the resistance arm is longer. That's going to change how this lever system works. Imagine if this was a seesaw in a park or something. If one person sits at this end and another person sits at the other end, how would moving the middle of the seesaw affect the weight balance? How would it affect how easy it is to go up and down? Would it still be balanced? What if you weighed differently to the person on the other end? Well, by moving the fulcrum, we start to move the effort arm and the resistance arm, the length or the distance from the resistance to the fulcrum and from the effort to the fulcrum. Second class lever, FLE 1, 2, 3, load is now in the middle. So if we were to move the load, suddenly that resistance arm is getting longer and our effort arm will have been reduced just by moving where that load sits. So if we had this person applying effort at one end and they're trying to lift that plank upwards, the effort arm is going to increase if we were to move the load nearer to the fulcrum. So the effort arm and the resistance arm Okay, it's the distance of those two components from the fulcrum. Third class lever, same again. This was our third option from that person trying to move the box. A person sat in the middle applies effort upwards, and the load is at the end. Well, if that person was to stand really close to the fulcrum, if that person is standing really close to the fulcrum, then it's going to generate a different sort of lever system. It's going to generate a different structure. We're going to have to change the forces in to get different forces out. Okay. So, mechanical advantage. What is a mechanical advantage? Well, we know effort arm and resistance arms can change from one lever to another. Well, if we can create a scenario where we are mechanically advantaged, then we're going to be able to move or get a bigger output from whatever it was that we put in. So it describes a lever which can move a larger load than the size of the effort applied. So if we go back to that person trying to move the box, because of the way that they set their lever up, so if I quickly jump into this one, this person, or option one, they put that fulcrum really close to the load, to the box, creating a really short resistance arm. And that left them this long space, this large effort arm, spin it around, this large effort arm on it, doesn't need to go down, which we can then apply force through and move that box. Now, that box I think was 250 kilos, 250 kilograms. Now that person pushing down with two hands, they're probably not, well, they won't be needing to generate 250 kilograms worth of push force to move that box because of the way the lever is set up, because of the distance of the effort arms and the resistance arms. If we were to move FLE 1, 2, 3, if we were to move this or change the shape of this second class lever system, even if the load was all the way up the other end of the plank and we applied a force upwards, well, we still got a bigger effort arm than we have the resistance arm. So we're still going to be able to move more weight than we actually need to apply force into the lever with. And that's what mechanical advantage is. If we can use the structure to our benefit, if we can put force in and whatever that force is, move more or overcome a greater resistance because of the way the lever system is set up, it's mechanically advantaged. If it's the other way, it's mechanically disadvantaged. Right, jump back in. Right, so how can we link levers into sport? Well, before we go there, how do we work out what the specific mechanical advantage is? Well, we know it's to do with effort arm and resistance arm. We know it's to do with if it's to do with it being close or more than or less than. Well, if we divide effort arm by resistance arm, we're looking for a score of greater than 1. So right now, if we take this as the example, onto this page here. At the moment, let's just say we've got this lever system. Okay, let's apply this to the body. Let's say that this is 6 centimeters. So it's FLE 1, 2, 3. Fulcrum is in the middle. Therefore, it's a first-class lever system. This could be our head. Okay, where the spine meets our cranium. Okay, that's where the pivot point is, and it can rock forwards and backwards like a seesaw. So it's about 6 centimeters. Well, if someone was shaped a little bit differently and the pivot point was here, well, suddenly their effort arm is very short. The muscles that they're contracting they're going to have to work harder to overcome not a lot of weight. effort arm divided by resistance arm. So if we were to do 1 divided by 5, so 0.2. So it's nowhere near 1, therefore we're quite mechanically disadvantaged. If we were to slide it back, and it was balanced, about 3 centimeters either side, 3 divided by 3, 1. So whatever force we put in, that's the exact amount of output or resistance we can overcome. Input, output are matched, they're equal. However, if we were to increase it now, whereby we've got 5 centimeter of effort arm, and we've only got 1 centimeter of resistance arm, 5 divided by 1 equals 5. That's much greater than 1. We're mechanically advantaged by 5 times. So we can put in a force of 10 and we can overcome a resistance of 50, roughly speaking. Okay, numbers aren't always going to be exact like that, but it just gives you an idea of how we can gear lever systems to help us. Now, what's the benefit of that to sport? Well, if we're mechanically advantaged, we don't need a big muscle to produce a big output. So a smaller muscle can generate a large amount of force to create a sporting action. For example, in our feet, which I'm going to get to in a moment. So how do we calculate mechanical advantage? Effort arm divided by resistance arm. We're looking for 1, but greater than 1 is mechanical advantage. We don't need to put in as much effort to move more force or to overcome more resistance. So a score greater than 1 makes the lever system mechanically advantaged, and it will mean that a smaller muscle can move a larger mass, and that's what I said there, the foot or the ankle. So levers in the body, last part, levers in the body. Well, how do we correlate a lever system to the human body? Bone, joints, muscles, objects. Bones, they're the rigid levers. Fulcrums, that's the joint, that's the pivot point. That's where bones articulate against and around each other. The effort, that's produced by the muscles. So muscles pull the lever, they pull the bone. The bone rotates around another bone at a joint or the fulcrum. Why do we do that? Well, it's probably going to be because we need to overcome a resistance. Just me here standing onto my tiptoes and back down, I need to overcome the resistance of my body mass being pulled downwards by gravity, my weight. So I have to overcome that resistance using a lever system, by using a muscle to pull on a bone to rotate or to pivot so that I can generate a movement. So the first class lever systems, 1, 2, 3. First class lever systems, FLE 1, 2, 3. So fulcrum in the middle is a tricep extension. So in the elbow, okay, we're talking about here now. So in the elbow, as the tricep pulls down, so this tricep contracts, it pulls on the lever, which is my radius. So that's my lever, and the tricep is pulling on the bone. Now I know the tricep's down here, but the effort point, so where you would draw the arrow from, is where the muscle attaches or inserts. Think back to last lesson, where the muscle inserts onto the bone and where it pulls from, that's the effort. So that's going to be at the very end of the radius. Okay. Now the pivot point is a little bit inwards, where the radius meets the top of the base, I should say, of the humerus. So we've got radius coming across, the humerus coming up, almost making like a T. Now this radius sits on top of the humerus, so it can then be pulled down and it extends. First class lever system. So an elbow extension, the tricep pulls on the radius pivots on top of the humerus or the fulcrum, and the hand is able to move upwards. Now whatever you put in the hand is then the resistance. In sport, basketball free throw. Basketball is the load, tricep contracts and it pulls its radius up, and we overcome the load or resistance at the right amount so the ball travels towards the hoop. Second class lever, FLE 1, 2, 3. L2 is in the middle. So the load is in the middle, fulcrum and effort at the other two ends. Just like in our foot. Have a look there, look at the foot. So where we stand, Okay, the ball of our foot, where it meets the floor and is going to allow that rotation, that's going to be our fulcrum, our pivot point. Our gastrocnemius, our calf muscle. Yes, it's located up towards the back of our knee, but the tendon where it attaches onto the foot, the heel bone, is right at the end again. So we've got fulcrum one end, tendon attachment or insertion at the other end, and that's the length of our foot. That's our lever. So all of the bones in the foot make up this rigid structure, this lever. All of our body weight is being experienced through the center of the foot. So the load is coming down through the center of the foot. There it is. Fulcrum at one end by our balls of our feet. Gastrocnemius at the other end pulls up, and we've got this tipping action. And as we do that, the ankle joint articulates, and it has that net effect of us going up. Second class lever, gastrocnemius at one end pulling up at the very end of the lever system, our body mass in the middle, and then the ball of our foot acting as the fulcrum. So plantar flexion, going onto our tiptoes. Gastrocnemius pulls, that's the effort. The rigid foot, that's the lever. The fulcrum is where the ball of the foot meets the floor, and then the gravity acting on the person's mass, creating that weight, is coming down through the center of the foot. Just like in takeoff. This could be triple jump, long jump, jumping to receive a rebound in netball, anything. Okay, whenever we're plantar flexing, we're applying force through the ball of our feet to try and move ourselves forward. Third class lever, third and final one. We're now dealing with the bicep. Okay, the bicep. Now you might be thinking, especially if the position is here, the bicep is behind the elbow joint. So surely it's at that end of the lever system. FLE 1, 2, 3. Surely effort is a third class lever, so it's going to be in the middle. But it is, because the bicep tendon goes across the joint and it inserts around here. So now we've got the bones meeting, the fulcrum, effort in the middle, load at the end. F-E-L. E is in the middle, therefore it's a third class lever. That's where the tendon attaches onto the lever that's moving. So the bicep, that's producing the force for contraction, that's the effort. The radius bone is the lever. So the radius here getting pulled upwards. It's rotating around the base of the humerus, which is coming down here. Humerus meets radius, so that's our pivot point. And then our load is whatever we put into our hand. Where do we use this? Any time that we flex our elbow. So it could be rowing. It could be swimming when we pull through. It could be tug of war. It could be golf, where we go from our starting position, we flex up, we push through with tricep extension, and then we flex again. So, to summarize, to bring all of this back round together, we've got three classes of lever system. 1, 2, 3. That thing down in the bottom right corner there, FLE 1, 2, 3. The middle component tells you what class it is. That's the secret formula. Just remember that. FLE 1, 2, 3. Whatever it is in the middle. That's what lever system it is. And then mechanical advantage. We require the effort arm and the resistance arm. We divide the effort by the resistance. And if we're mechanically advantaged, that will give us a score of greater than 1. And what that means is that we don't have to put in as much effort to move more weight. So less force in gets a greater amount of force out. Mechanically disadvantaged, we have to put more force in to what we can overcome. Okay, and that is mechanical disadvantage.